Okay, so time to get started. Let's see here. So here's where we were last time. We were talking about triple integrals. And remember, the big idea of triple integrals is that we might have not a one-dimensional, not a two-dimensional, but a three-dimensional. I'm having coordination problems. Three-dimensional domain over which we want to make some sort of a chop it up, add it up kind of an argument. In other words, we have some sort of an accumulating quantity where the whole is the sum of the parts, and you can chop the question up into a bunch of little pieces and then talk about on each piece, such as, for example, this little piece. And, well, how much of our accumulating quantity is on that little piece is a much easier question and can be, hopefully, presumably, possibly, broken down as quantity per unit volume times volume. Right? That's the dream. That's what we're hoping for when we do a Riemann sum argument. And then you add up over the entire three-dimensional domain, and that's the strategy for answering a question of this sort. Okay, so the note we talked about all this last time. This is about where we left off. That we're going to use this notation to represent this Riemann sum expression again, which is just a mathematical expression of, I want to take my problem and chop it up into little pieces because the whole is the sum of the parts, and on each little piece it's a simple product. Okay. All right, so again, this is where we left off right before break. I hope everybody had a good break. Welcome back. Okay, so let's put this into action. This first example is, we've kind of already done it in the sense that mass is always my favorite kind of metaphor for an accumulating quantity because it's viscerally relatable. I just like it, right? And so, okay, suppose you want to compute the amount of mass in some rectangular box region. Well, the whole is the sum of the parts. That's basically what this says right here. This is just the observation that mass is an accumulating quantity, which it is. Right? You'll notice I'm using integral shorthand. It's convenient and common, and I encourage that. A little sloppy, but it's awfully convenient. And then on each little piece, no challenge to see that on each little piece, the amount of mass there is on each piece is, well, mass per unit volume times volume. And, again, that's what we mean when we say per unit, right? When we say mass per unit volume, we mean that which you multiply by volume to get mass. Okay. All right. And then, lo and behold, we have a triple integral. And then the question remains how to compute that, and we'll get to that in a couple of minutes. All right, so millions of other examples that you can probably imagine. Before we get into more details, I do want to give you all a warning. Maybe I'll start like this for dramatic reasons. So how to think about this geometrically? What's the picture that you should have in your mind? And I want to give you all kind of a warning. This is everybody's favorite picture of how to think about a single variable integral, right? The area under the curve. And then this is what we extended to make sense out of double integrals, right? Our sort of first question that we even entertained that eventually led us to develop double integral volume under a graph surface. So in both cases, graphs. In both cases, how much size appropriate to the context? How big is it, right, underneath that graph? Okay. All right. Now, we have an alternative point of view for each of these. You can view single variable integrals as being, for example, mass of a rod is, again, my favorite sort of first example because, mass per unit length times length and all that. Right? And so I have mass accumulated on this interval on the x-axis. There is no two-dimensional picture because there's nothing in the question that's two-dimensional. Right? We're just f of x dx is representing density times size here, and then we're adding up over the whole thing. Okay, likewise, You can think of a double integral as representing, well, just the amount of mass accumulated over a two-dimensional region. Tallest to sum of the parts. Again, there's no need to talk about volume here. There's no volume in the question. Okay. All right, so pros, cons. Which one do you like better? Is there a certain amount of subjectivity to that? I do want to encourage everybody to think about everything from the point of view of mass and not graphs. Because graphs only come up sometimes, but we're always accumulating stuff. So this is a more universal point of view. Again, it's not what you see in Calc 1 classes. In Calc 1 classes, they are very myopically focused just on this one little story right here. Right? This is just all they want to talk about, and so you don't have to worry about other situations and other problems that may arise. So here's the problem that arises. Let's think about this point of view again. We have a one-dimensional integral, and the picture we have to understand it is two-dimensional. Okay, two-dimensional integral, the picture we have to understand it is three-dimensional. I'm sure you see the pattern. So if I want to make sense out of a triple integral, well, look, you should expect this to be a four-dimensional picture, and that's losing. Right? There's no way. I can't visualize four dimensions. You can't. We're not that kind of critters. We're not built for that. Right? So this is another argument of why I discourage this graph point of view on integrals. It sets you up for an unsustainable pattern. You can't take this idea of single variable integrals, this idea of double integrals, and make sense out of it in this sense for triple integrals. It just doesn't work. Okay, so now let's think instead, though, what about this accumulation point of view, this mass point of view? Well, one-dimensional integral, one-dimensional picture, two-dimensional integral, two-dimensional picture. For one thing, that's very natural, right? It fits, right? One-dimensional to one-dimensional. That's just natural. And then so you get to a three-dimensional accumulation, and you have a three-dimensional picture. Perfectly doable. I guess a little artistically challenging sometimes, sure, right? But perfectly doable. So this is a sustainable point of view. So anyway, that's just my constant pitch to think about integrals from kind of that point of view. One last little observation I'll make before we go on is to address a question that I get very commonly in multivariable calculus classes, and it roughly goes like this. How come sometimes a three-dimensional picture represents a double integral and sometimes it's a triple integral? How do I know whether I get a double integral or a triple integral? And you can see why they would be confused. After all, this is a three-dimensional visualization of a double integral. This is a three-dimensional visualization of a triple integral. They're both three-dimensional. Right? And the answer, the resolution, I guess I should say, of this seeming conflation is that this is apples and oranges. They're completely different kinds of pictures. The one on the left is a graph. The one on the right is not. This is just a domain. So definitely different, and anyway, a possible source of confusion. So to the I know that y'all are not going to let go of this. I accept that. Right? And okay, that's a good thing, I suppose. And I guess likewise with the one below. But I do hope that y'all will try to, as much as you reasonably can, buy in to having three in a row, consistent comfort with visualizing all these kinds of integrals in this consistent way, because this really is going to be very, very common and stuff we're going to do in this course. Okay. All right. So, moving along. All right. Now, let me focus on this diagram for a moment. I think I can probably fit. Yeah, there we go. So y'all probably recognize this diagram, or at least it looks a lot like a diagram that we talked about back with double integrals. Now, there are a few things that are different on this diagram. So this right here is where we had previously talked about volume under the graph of a function of two variables. Well, for triple integrals, this would have to be, well, let's see, the graph of a function of three variables. This would be like four-dimensional volume or something like that, right? Which, again, we can't really make sense out of. Now, it's not that it can't be done. It can totally be done, but this is not the course for it. Okay. So I'm going to say we kind of can't make any sense out of this, certainly in this context. So as a result of not being able to make sense out of that, I certainly can't make any sense about an argument that would purport to directly connect to it. That's obvious, right? I also can't use an idea that I cannot understand to connect to these kinds of constructions we've talked about, as was necessary for us to make the connection that double integrals could be computed with iterated integrals. Here's the thing, though, even though I cannot make this argument here, the result is still true. And there is a perfectly, in fact, the honest, rigorous proof of this fact, even for double integrals, doesn't involve this in the first place. There is a directly algebraic argument that you can make that shows that these are equal, as we have here. That argument is unfortunately highly algebraic and with some formal sticking points that I think are more of a distraction than a help in this class. So again, I don't think this is the right context for making such an argument. I'm just going to assert that this is true. I hope you're willing to buy it. It is perfectly analogous to the conclusion we got for double integrals. It's exactly what you would expect. I think this is pretty believable. I hope you're on board with that. And I got ahead of myself. Of course, again, you cannot make any immediate arguments about how mass is an iterated integral, because if you look within the expression, you'd find mismatches you'd find at some point you have quantity per unit volume times length, and that doesn't make any sense. That's not something we have previous experience. We can't make arguments about that because we don't understand that. Okay. All right. So, but notice we're still basically good, because as I already have shown that mass can be written as a triple integral. I think we're bought in on the idea that triple integrals can be computed with iterated integrals, and as is always the case, we can compute iterated integrals with the fundamental theorem. So we can still totally do this three-step process right there, just like we did for double integrals, and that's still going to be what we're going to do. This is how we're going to use triple integrals to solve problems. Same basic roadmap. Okay, let me pause for a second. How do we do it? Is everybody on board? Any questions? Okay. All right. Okay. So now, just as an example of how the computation breaks down, let's talk about that right there. How do I compute an iterated integral to get an answer? Most of what we have here is that. I guess I shouldn't get too far ahead of myself, though. We are first, as previously argued, turning mass into a triple integral. As I claimed above, we rewrite the triple integral as an iterated integral. And then all that remains is what I have in orange here, using the fundamental theorem to crank that out. And that process is just like with double integrals. It's starting with the inside, working your way to the outside. And so let's see here. We'll start with this inside integral. Keep in mind that inside integral has z as the variable. That means that x and y, being further to the outside, are constants. That means that this xy right there, this is not a product of several factors of expressions of variables. Not at all. This is a constant times z. Right? And constants just kind of come along for the ride, and of course 2z, its antiderivative with respect to z is z squared, and again the constant comes along for the ride. Cool? It's just like with double integrals. Everybody happy? All right, et cetera, et cetera, et cetera. Good exercise. Follow this all through. Make sure that that all makes sense. Make sure that you can do that yourselves. Good exercise to fill in those blanks. Okay. All right, now what do we do with non-rectangular domains? Here is another instance where I'm not going to be able to give you the same arguments that we did when we were looking at double integrals. Just think back for just a quick moment. How did we approach non-rectangular domains for double integrals? Well, I drew one. In particular, I drew a volume under a graph over a non-rectangular domain, and I visually sliced it, and we looked at what those slices look like. And we came up with an argument about how to find the bounds, et cetera, et cetera. That would be a four-dimensional picture. Again, I can't give you that argument. It remains, though, that the process is totally analogous. And so, again, I'm just going to ask you to take this on faith. All we need to do is look at the, whoops, I got ahead of myself. We just need to look at the domain. So let's suppose we have a three-dimensional solid like this. We're going to go through the same process of pick an axis to slice perpendicular to. We'll identify the starting and the ending slices. Those will be our bounds for that integral. And then we'll fix a slice at a generic value and then repeat for the next variable. Namely, we'll slice orthogonal to that axis and then identify the bounds and then fix a slice of that, et cetera, et cetera. You just keep going. All right, so geometrically what that looks like, let's look at this picture here. Three-dimensional solid. Oh, and I should say, for no particular reason, I'm going to, as this first example, I'm going to do my slicing in this order. Keep in mind, we always, when it comes to slicing, we start on the outside and move inward. Only when it comes to evaluating do we go to the inside and move outward. Right. So starting on the outside, we're going to do our dx slicing, followed by dy slicing, followed by dz slicing. Let's just remember that. Let's see here, and let's do it. There's the x-axis. Here's a slice by a plane perpendicular to the x-axis, and a geometric appeal. What that's going to look like is something like that. Some sort of a shape. By the way, this is just an arbitrary figurative shape. The particulars, we'll get into particulars later. But anyway, that's what one of those cross sections looks like. Now let's ask first and last. What is the first of all of these slices? Where is that on the picture? Well, it's going to be back here. Some little, whatever point is furthest back into the screen. There's some point there, and that point is going to be what I'll use to determine my x1. And where's my last slice? Well, again, as I'm doing these vertical slices perpendicular to the x-axis, there will be a last one, and it'll be like, let's say maybe there, and that will give me my x2. It's just like with double integrals. It's just three-dimensional instead of two-dimensional. Is that all cool? Okay. All right. Right. So now, again, per the procedure, we fix a value of x. We focus all of our attention now on this slice. Only interested at this point on what's happening on that slice. and then we move on to the next variable. So the next variable is, let's see, I'm going to switch to pencil mode. The next variable is y, so let's keep in mind there's the y-axis. Artistic challenge. Here's what a slice perpendicular to the y-axis looks like. Geometric appeal, there's no getting around this. You got to visualize this geometrically. What does it look like if I take my existing x slice and then do a y slice of that x slice? And here's what I assert. I'm going to get a little line segment like that. Slice perpendicular to the y-axis of our initial slice perpendicular to the x-axis. Everybody see that? Just geometrically? Yeah. Okay. All right, so now again, we got to think about first and last. And let's see if I can delete. Yeah, there we go. Okay, so first and last. Well, the first y slice is going to be at some point, sort of the far left point, if you will, on that x slice. And that will give me a y1, and then there will be a last slice, kind of the farthest to the right point on that x slice, and that will give me my y2. Everybody with me so far? Let's think about what this depends on. Is y1 just some number? Is it just, can I just solve for y1 and it's just going to be like 7 or something like that? No, not at all. It's going to depend on x. Now, again, geometric appeal. Let's look at this picture. We've got this lump of a solid. When I take an x slice of it, I will get some sort of a shape. I'm going to get a different shape for different values of x, right? If I were to pull x further out, then that slice would get, as I have it drawn here, anyways, kind of smaller and smaller. And these purple and dark blue points are going to move depending on x. And so those y bounds depend on x. They are functions of x accordingly. That makes sense to everybody? Okay. Okay, now per our procedure, we're now going to fix, in addition to x, we're now going to also fix y. We're going to fix a specific y slice of our existing specific x slice. Let me write that a little bit differently. Having fixed both x and y, it's like I'm going to fix a point down here in the xy plane, and I'm going to think about the points in the solid that are, that are directly above that point in the xy plane. And I want to think about, okay, again, where do we start? Where do we end? Well, that's where z starts. Here's where z ends. And notice where z starts and where z ends. Well, that's going to depend on this point down here in the xy plane. What is the arbitrary x that we're at? What is the y that we're at? As x and y change, this point down here moves around in the xy plane. Well, then we're going to get totally different little slices here, and we're going to have different starting points, different ending points. So they're functions of x and y. Yeah.
Are we slicing that one
perpendicular to the z-axis? That's right. Yeah, but you don't even have to think of it as slicing, because we're chopping it into little pieces, sure, but it's not like we need to have a slice that we can multiply by thickness to get area or volume or something like that. We just need to keep track of the pieces themselves. Yeah. But morally, yes. Okay, so as a result of that geometry, here's what our iterated integrals are going to look like when we have non-rectangular domains. We're going to have, for example, our inside integral, the bounds are going to be functions of the variables further to the outside. Okay. And in the integrand, we treat the variables further to the outside as constant because they are for the purposes of that integral. Does that make sense to everybody? All right, so that's the process. And we're about to jump into one. I do have some just sort of real quick, broad advice to give before we get into that. And again, all of this is kind of a rip-off from double integral.
So the weight, is there like a specified weight to like split it between like Z1 on the Z's from the outside and Z1 on the inside?
I couldn't understand. Say again,
Is
please.
there some specified, can you elaborate more on how to split between Z1 and Z2?
How to what now?
Like split it between Z2 and Z1?
I don't know what you mean by split it.
Because that looks like a circle, right? So would you just have it from like, let's say...
Oh no, this is just a generic shape. It happens to look vaguely circular, but it's not a circle. So the point is the geometry of the question will tell you how to identify these points. I can't specify here because we don't have any knowledge of the nature of the shape. Does that make sense? Yeah, okay. So yeah, let me do some examples. Let me see if I might inadvertently answer your question. Yeah. All right, yeah. Okay. Right, so yeah, a couple of broad strokes though, again, pretty much stolen from double integrals. When we construct the iterated integral, we start on the outside, we move toward the inside, just like with double integrals. Bounds are functions of variables further to the outside, just like with double integrals. And how do you find bounds? Well, you look at the corresponding points. You identify them as being on certain geometric objects. These are now surfaces. Those surfaces will have certain equations. That gives you algebra in which you can solve for what you need. Okay, so all of that is kind of rip-off from double integrals, and we will rip off more in just a minute. Okay, so here we go. First example. Okay, so here's our domain for some sort of a triple integral. Now, why am I interested in this triple integral? Where did this triple integral come from? Let's not worry about that. Let's suppose we've got some application and we've got some resulting triple integral, and we're just trying to figure out how to convert triple integral into iterated integral. So maybe this represents a mass, maybe it represents a number of mosquitoes in the room, or so, whatever, right? Okay. All righty. So I claim that this is a tetrahedron. This is a good little geometry problem. You can persuade yourself, for example, x equals 0 is this plane back here, and likewise for these other coordinate planes, and then this is this plane like that, and all together we get this tetrahedron that I have drawn. I hope that geometrically makes sense. By the way, the geometry, taking the algebra here, right, and inferring what the solid actually looks like that's again your job, right, as a question answerer, right, as the student taking the test, is to be able to take algebra and phrasing like this and produce the picture. So think about what you recall about the equations of planes and that sort of stuff, and this is what you get. Okay. Now, no particular reason. I'm going to do my slicing in this order. Yes, there are 5 other ways to do it. We will talk in a few minutes about some considerations, some strategies for how to make choices, how to make good choices on which order to do your slicing. For the moment, let's just take this as a given. I just want to get one into the win column, get an actual triple integral turned into an actual iterated integral, and then we'll talk strategy. Okay. So, starting with dx. What's our x bounds? Well, there's the x-axis. Here's what an x slice looks like. And now geometric appeal. You're going to hear me say that a lot, by the way, because a lot of these questions are unavoidably geometric, right? And so geometric appeal, look at the picture, etc. Okay, so x slices look like that. Now where's the first one? And I claim it's back here. Now I could follow my own rules and write down what we know and blah blah blah. But it would be kind of silly because I just need to know what the value of x is for this first slice, and I can see that slice. And it's clearly in the YZ plane where x is 0. So how do I solve for x when I know x is 0? Well, that's pretty easy. It's just 0. So again, sometimes you get a freebie, and that's okay. That's a good thing. Okay, but no, where it gets interesting is if we try to make sense out of this last point. That point, that being our last slice, as we come out of the screen, toward you, as it were, where's that point? And that's not immediately obvious. But there's some algebra that I can write down. Now, again, following our procedure, that point, I've got to identify what geometric shapes can I see from the picture that point is on. And the first one I'm going to observe is it's on that face of my tetrahedron, which has that equation. Now, how do I know? Well, picture. Now, I cannot emphasize this enough. You've really got to have a good picture for this kind of thing. 2 reasons. First of all, that's where the choices come from. They come from the good picture, right? And then to the question of, well, yeah, but what if I can do that in my head? First of all, I'm really impressed if you can do that in your head. But anyway, to the extent that you might be able to do this in your head, keep in mind, you have to show your work and explain your reasoning. And if in fact, as I think is unavoidably the case, if your reasoning hinges on the geometry, you've got to explain that geometry. And I think it's going to be hard to beat a picture for that. So it's as much as required, not as a matter of policy, but just as a natural consequence of explain your reasoning. Show me that you know how to conclude what you've claimed. Does that make sense to everybody? Okay. All right, let's see. Now, what else do I know about that point? Well, again, thank you, picture. I can see it's on that face of our tetrahedron, and that face has that equation. Oh, and then there's another one I can tell, and again, you've got to have the picture for this. I can tell that it's on that face of our tetrahedron, which has that equation. So this point that I'm interested in, that's going to determine my x2, this is the algebra that I know about it. And just as a reminder, we followed our process. We're looking for a certain bound, which we relate to a point, which is on certain surfaces, which have certain equations, and now we just have to solve. Is everybody with me? Is everybody happy? Now, again, my little ritual. Oh, yeah, question.
You were just able to derive this with the graph or the you drove.
I was able to identify which equations to write down by identifying which surfaces the point in question is on, and what is the point in question, and which surfaces is that point on comes from the picture. Yes. Is that okay? Yeah. Cool. Okay, so my little ritual. Maybe this is just because I'm less intellectually organized than some. I'm open to that possibility, but I like to remind myself before I start solving, what is it that I am solving for? I think it's easy to forget and accidentally solve for y or something, right? You just get the wrong thing. So I encourage you to check in. Wait a minute, what am I doing? I'm looking for an x bound. So in this algebra, I'm going to solve for x. And pretty straightforward algebra. You get x equals 1, and that's why this upper bound is 1.
What's
Wait.
that?
I'm sorry?
What's that?
What's what now?
The function?
Oh, it doesn't matter for the question. It's the integrand for whatever application. Like if we're trying to compute mass, then this is mass per unit volume. If we're trying to compute population of mosquitoes, then this is mosquitoes per unit volume. Whatever. Yeah. Okay. All right. Now let's move it along to the y bounds. Let's see. Oh, first, of course, we've got to fix a value of x So we're now going to restrict our attention to a single x slice. Okay. And looking only at that x slice, let's think about y. So first of all, what do y slices look like? Well, they look kind of like this. Those are y slices of our x slices. Where's the first one? Well, it's there. There's our first y slice, where y is obviously 0. So again, sometimes the fish just jump in the boat. You got to love it when that happens. You just go ahead. If it really is painfully obvious, you don't need to do a bunch of algebra to document what you can straight up see out of the picture, right? So that's totally fine. Where's the last y slice? Well, that's going to be this point. And so now, again, we got to play the game. We got to look at this picture and ask ourselves, okay, what do I know about that point? Now, the first thing we know is kind of a repetition, and this is how I like to write it down. This is a silly way to write it down. I'm going to confess to that right off. Of course, x is x. It's tautological. It's meaningless almost. This is my little reminder to myself that x has been chosen. My answer will depend on x, so just leave x as x. Right? Now, this is my little reminder to myself. You don't have to do it like that, but it makes me feel a little bit more comforted to recognize that I've got that factored into my algebra. What else do we know? Well, the point in question is on that plane there, which has that equation. Again, thank you, picture. And it is on, let's see here, that plane there. Again, has that equation. So this point that I'm trying to understand to get my y upper bound, this is what I know. Reminder to myself, I'm solving for y. So I need to solve for y here. Wait a second, I need to solve for y, but it's allowed to be in terms of x. Because x is further to the outside, the y bounds can and should be a function of x. So I don't need to get rid of the x. And with that in mind, and a little bit of algebra that y'all are perfectly capable of, there's y as a function of x in this algebra, namely for that point, which represents our upper bound for y. So this is our upper bound for y. Everybody happy? All right. Yeah.
So we're always starting with a slice through x, like.
Oh no, whatever's your outside variable. I just happened to choose x here. But
Yeah, like we could have chosen any other.
Yeah,
It could
yeah,
have
yeah.
been y or z.
Could have been y or z. That's right.
Okay.
Yep. Yeah, I just wanted the first example to follow the pattern of the differentials that we had from this picture where we motivate, just to make it a little bit
Whereas
easier.
the x was on the outside.
Yeah, that's right. Which itself, now again, this was arbitrary, but yeah, that's all. Okay, and my next example will not follow that same pattern.
But whatever we take, we'll always get the same answer, I assume.
The iterated integrals, when evaluated, will always
Will
give the
have
same
to
result.
yield the same
That's right.
result.
Which they have to because they're computing the same thing.
Yeah.
Yeah, exactly. Okay, so let's talk about z-bounds. And again, now x and y are both fixed, so we're looking just what's above that point in the xy plane, as it were. And there's how z varies. You know what? That's a bad color choice. Let me do that in a lighter color. So x and y further to the outside. So looking just above that point. Okay, so where does z start? It starts there, where I'm going to say pretty clear that z is equal to 0. Again, sometimes you get lucky. This is a good thing. Go ahead and capitalize on freebies. That's nice. But what about the upper bound? Here we go. The upper bound for z is going to come from that point where I know three things. I know x and y already. X and y have been chosen. So that's I know what x is, I know what y is. What else do I know about that point? Well, I know that that point is on this plane here. That comes from the picture. Again, I cannot emphasize this enough, right? You really need the picture there. And okay, well, that plane has that equation. Now, in all of this algebra, let's see, again, what am I doing? That's right, I'm solving for z. Right, there's my little ritual to remind myself what we're doing. So I'm going to solve for z. It's allowed to be, whoopsie. It's allowed to be a function of x and y. X and y are further to the outside. And you see that is, in fact, what happens. That z is a function of x and y. And that, then, is our upper bound for z. How are we doing? Everybody see the process? Now, again, the algebra on this one was easy, right? The geometry wasn't particularly challenging. Still non-trivial, right? But this is by far not the worst geometry we're going to see. But the purpose of this example, the focus here should be on the process. Is everybody happy with the process? Okay. All righty. So, some points of strategy. You got 6 options on how to slice. You want to do your best to make good choices, right? You make good choices here and everything's downhill. You make bad choices here and it's going to be an uphill slog, right? And you're going to have various different kinds of penalties that you'll pay for making a bad choice. So how do you make a good choice? Just like with double integrals, try not to slice through corners. It's very likely to just put you into this weird situation where your bounds are going to be different for different sides of. You're going to have to break it up into pieces. It's not going to be nice. So try not to slice through corners to the extent you can. Think strategically about what you would like to solve for in terms of what, and whatever it is that you put on the inside. That's the one you're going to have to solve for. So put on the inside whichever one is more naturally a function of the others in an algebraically desirable way. So again, this is just, basic strategy of, don't paint yourself into a corner in some undesirable way. This last little bit isn't going to make sense until I show you an example. So for the moment, I'm just going to say, we're going to come back to this. We're going to basically motivate this bullet point here through the following example. And this one's harder to draw. And it's going to be a little bit harder to think through the algebra of it. The geometry of it. So here we go. By the way, before I get into the math on this one, that's a pretty decent picture, I think. Yeah. It took a long time for me to draw this picture this decently. Notice I don't say well, right? It's not like this is a beautiful work of art, right? But this is good enough for our purposes. It kind of conjures this three-dimensional image that we need to be able to understand and work with. Okay, how do I do that? Right? That's hard to do. So there's a lot to say about how to make a good drawing. I spent a bunch of time a few years ago thinking through, wait a minute, how did I do that? Right? And kind of trying to document everything that goes through my mind when I make drawings of this sort. And then I made a couple of videos where I explain in, I think, great detail everything that I know about mathematical drawing. And in fact, this diagram is one of the diagrams that I draw as an example in these videos where I talk about mathematical drawing. As I draw this, I explain not only what I'm doing with pretty much every stroke of the pen, but why I'm doing it with every stroke of the pen. Right? I think it's if you're already happy with your mathematical drawing capabilities, no problem. You don't have to do any of the following. But if you wish you were better at mathematical drawing, or if you are bad at mathematical drawing, whatever. This is something that has to get fixed. This is not an acceptable state of affairs. This material that we're doing is intrinsically geometric. The ideas you're going to have to argue are intrinsically geometric, and to communicate ideas about unavoidably geometric things, it's hard to do that without drawing, right? So I think this is a borderline essential skill, and again, if you're not good at it, then it's something you need to work on. So if you want to see everything that I know about mathematical drawing, it's again in those videos. So on my YouTube channel, obviously, there's a playlist called Miscellaneous Topics. You click on there. It's perfect. I think they're called Drawing 1 and Drawing 2 or something like that. Not very creatively named. But give those a look. I hope you'll find those helpful. Okay, so let's dive in on this. This surface is a paraboloid. Y'all remember paraboloids. We're only looking at the part in the first octant. That's why we're only looking, positive x, positive y, positive z. Not that there's any negative z's here, but anyway. And let's see, capped at the top by z equals 1, which is going to be kind of like that. So this is our figure. I hope that makes geometric sense. Again, keep in mind, it's part of the problem is to figure out how to understand what these things look like. So you got to give yourself practice in taking algebraic descriptions, and then producing the resulting picture. Okay, now right off the bat, this leaps off the page at me. Right? I mean, looking at this equation here, just trying to anticipate. Look, I know eventually I'm going to have to solve for something in terms of other things. Would I like to solve for x in this equation? No. Gosh, I hope I don't have to solve for x in this equation, because that means I'll have square roots in my bounds, which will then be square roots in my subsequent integrands, which will make those integrals brutal. So I don't want to solve for x, and I don't want to solve for y. I am pretty okay with solving for z. Partly because it's already done, but that's really not the point. The point is that there's no square roots when you solve for z, right? So that motivates putting dz on the inside. And that's just a motivation. I can't prove that that's right, but that's a pretty good motivation. Is everybody all right? All right, so I claim that this sets up what I'm going to call a good projection into the xy plane. And so this is, what I'm talking about up here. And there's various aspects of what qualifies to me as a good projection. And let's go through these one at a time. The shadow is nice. Let's think about the shadow here. In the xy plane, our shadow is this. And that's not so bad. I mean, all else being equal, I like rectangles, but this isn't, it's not that nice, but it's just not that bad. Okay. Now, who cares about the shadow? We weren't asked a question about the shadow. We were asked a question about the solid. So why am I interested in the shadow? And here's the reason why. If you look at your solid, right, and you think about what these slices look like, every slice of our solid corresponds to I'll say it this way, every slice of our solid has its own shadow. And that shadow of that slice is itself a slice of this shadow. And so as I slice up the solid, I am effectively slicing up the shadow. So I claim the range of values on the solid are exactly the same as the range of values on the shadow. It's fantastic. Right? So I don't need to think about this solid. And by the way, it's pretty hard to draw the slice here. You really got to think it through. And it's easy to mess that up and to get geometrically confused and get in some trouble just for geometric and artistic reasons. Right? but you don't have to. All you need to do is just look at this shadow. This shadow's a quarter disc. And how do we slice up a quarter disc is pretty straightforward. This is just basically a double integral argument, right? We've sliced up two-dimensional regions and gotten bounds many times doing double integrals. So I think this is a beautiful little strategy that we're 2/3 of the way done, and we basically haven't even looked at the three-dimensional solid very much yet, just enough to be able to draw what its shadow looks like. Everybody on? It's pretty cool, isn't it? Right? It's nice. And again, you don't have to do this if you want to draw the slices and do all the three-dimensional stuff. Go ahead, right? But it is going to be a lot more challenging in multiple ways. And I see I'm out of time. Okay, so we'll pick up here. We'll pick up here next time. Y'all have a good one. Again, don't forget about attendance, and we'll see you on Friday. Let's see here.